Hello everyone, this is Shilpy Bhullar and here I am with another video which is based on divergence of a vector function. As you all know, we are doing our lecture series based on vector analysis and we have just done line integral, surface integral and volume integral. We have already done divergence and curl of a vector function mathematically, but now it's time to understand the physical significance of divergence of a vector function. So let's get started. This spectacular picture that you are seeing, this giant hole, it is known as Glory Hole, which is a man-made hole at Lake Berryessa, California. Officially, it is called Monticello Dam Morning Glory Spillway. It's designed to keep the dam from overflowing and thus acts like a drain, a sink. So instead of drain at the bottom of the lake, this has been designed at the top of the lake. It sits at the top, as you can see. And whenever water rises to a certain level, it just flows through it and the level is maintained, whatever fixed level is there. So it's indeed a very spectacular and amazing man-made creation. But for me, this gives glimpse of something related to divergence of a vector function. You all know what are vectors now? Physical quantities which have both magnitude and direction. So if something is flowing, suppose whether it's liquid or gas, any quantity, any fluid is flowing and it is having some particular direction, then we can consider it to be a vector. And if water is flowing and it is flowing in some particular direction, we all know water is the best example. The flow of water, the flowing water is best example of vector function because it flows and we can measure its magnitude and we also know its direction. It flows in a particular direction. And thus I find it a very good example to understand divergence of a vector function. As we have discussed, that generally this term divergence means spread, how much the vector function is spreading. But this spread or this divergence is not only a positive divergence or simply that something should spread. In fact, something can converge also. That will also be considered to be divergence. So divergence is more like a common big term and we use it for both spreading and converging of any vector function. It's all about, it tells us that whether something is flowing at the same place or is it just spreading out or converging to a particular point. If water is flowing, suppose we have some pipe and this water is flowing and this is the opening, okay, and now through this opening the water is still coming at the same pace. It's not spreading, it's not converging, then we say it's not diverging at all. That the divergence is zero. First, let's see what's the definition. How do we define this divergence of a vector function? Now, vector function, we know we take some region and we say that the vector function or the vector field is just spread over that region. Like suppose this water is vector function. So this whole lake portion, this is the place where this whole vector is spread, right? So it is spread all over this region. And then what do? We always pick some particular portion. We consider that, okay, let's find the value at this particular point. All right. And then we try to integrate it for the entire region. It is not possible for us to find the value at like for the whole region in one go. It is just not possible. So what do? Now here, since you can see it looks like surface. So then we might use surface integral. Okay. We will pick a particular region, some particular surface element, and then we'll try to integrate over the entire surface. But then there is also possibility that if we are considering small closed surface, then it might be enclosing some volume also. And you know, in lake, there is some depth also. So it just encloses some sort of volume as well. We know that it's not just that water is only spread over the surface. It's everywhere. It's beneath the surface also. So there is volume capture as well. But still, when we solve, we try to consider a very small surface element, and then we say that it encloses a very small volume such that the volume tends to 0. So we say that volume tends to 0, often denoted by this. So that means that it is very, very small, negligibly small. It is not 0, it is only tending to, it is approaching 0, but it is not 0. So that means that whatever volume is being considered, it is very small, infinitesimally small, right? This is the word that we use. Let's see, it says that let A be a vector function in certain region of space. So suppose here this A is a vector function which is water. So let's water be the vector function A, which is spread over this region. As you can see, this whole space, everywhere you can see the water. The divergence of A at a certain point P, so we will pick some point, is defined as amount of outward flux of the vector field A per unit volume as the volume enclosed by the surface tends to 0 surrounding the point P. So whatever point we have chosen, we say that there is some volume as well. So amount of outward flux, something, flux is what? It's number of field lines passing through a unit area, passing per unit surface, we say. So how many lines are passing through a particular surface? And that is outward, means they're just going out. So we say that if whatever region we consider here, suppose this is the particular region, this region we have picked, okay, and then we say that what we will try to find, what is the amount of water which is just moving through this surface. So what is the outward flux? Outward means what is just going through this surface. And then we consider that, okay, whatever surface element we have picked, it encloses some volume. So like you can see, it's a 3D portion that we have considered. So it just encloses a very tiny amount of volume, but the whatever we are considering, it's around this point only, point P, that's it. So if dV is infinitesimal volume enclosed by this small surface, which is a closed surface S surrounding the point P, then the divergence is defined as its divergence of vector A, which is simply del dot A, that is equal to limit, since we said that volume is approaching to 0. So that means whatever volume, the smallest portion that we are considering, it is tending to 0. The volume enclosed is very small. So this is the meaning. And then we say this A dot ds, which tells us the amount of outward flux of vector field A, and then it says per unit volume, so we have to write dV in the denominator. As you know, the flux, this word, the first time we read this word is in magnetic field chapter, and we say magnetic flux, number of magnetic field lines passing per unit area, and we often define it as phi is equal to B dot A, if you remember. And this, what is this A? This is area. We often write it as B dot ds also if we consider a small surface element. So same thing is here. There we used to deal with magnetic field lines. Here we are considering some other function, and this vector function could be a water, could be a liquid. So this is how it is. So whatever amount of vector field is passing through that small surface S, per unit volume, like because that surface S is enclosing a very small volume which is tending to 0. So through that volume, how much amount of vector function is passing through? This is what we mean by divergence. Basically, it just discusses with how much a quantity is flowing through a particular surface per unit volume, because that surface is a closed surface and it would definitely enclose some volume. So how much amount of vector field lines are passing through that surface per unit volume. If you consider any surface and then you say how many field lines are just passing through this surface, but we also say that that surface encloses some volume. So that's why I'm showing this thickness also. So this is what do we mean by divergence. Now this divergence can be of many types. If something is flowing, we are talking of outward flux. We are just considering that the vector field lines are passing through that particular surface. Now the way they pass through that surface, that can be of different types. One thing is that the way it's entering in the same way it is moving out. Other thing is that it is entering in like a normal thing, but when it moves out, it just diverges. Okay, this can also happen. Or what can happen, like they are passing normally in the sense that just in normal state, that you see it's just a plain flow, a laminar flow, and then after passing they just try to converge to a particular point. So all these are different type of divergence. See, in the mirrors chapter that we studied in class 10, we have a particular notion about convergence and divergence. We used to study that in concave mirror, we have that the rays actually converge to a particular point called focus after reflecting from a mirror, and in convex mirror the rays diverge. So we had that particular notion about convergence and divergence. But here when we say divergence of a vector field, then it includes everything. Divergence include divergence also, which actually means to diverge, and it includes convergence also. It just deals with that how the vector field lines are behaving. Either they are just diverging after passing through certain surface, or are they just converging after passing through certain surface, or they are just passing normally, like the way they were entering in the same manner they are coming out. This is what divergence deals with. Divergence of a vector function is a scalar quantity, we know that, and it is simply an operator. You know that del vector, the del operator, is simply an operator and has no meaning. It's only when you attach some physical quantity to it that its meaning come into action. So del, when applied to any vector function, whether you are applying it via dot product or cross product, its meaning changes. Now just to understand this further with an example, again I'm going to consider this picture. But here you can see this first picture that I'm talking of. If I have to consider that, okay, I'm considering my vector field, the vector function to be water, a fluid. And then I have to see what different type of divergence can that liquid show. Now you see this opening is very small. Obviously, behind this opening also it would be a tiny, or you can say a narrow path, a narrow tubular path would be there. So water would be just coming. But now you can see the moment it comes out of this opening, this is the opening and water is coming out of it, it is diverging now, it's spreading out. So the amount of outward flux per unit volume of the surface, it's actually telling us that the moment water passes through this surface, it just spreads out. You can see, obviously the opening is very tiny, so you cannot expect that this much water would be coming from there. No, Behind that, maybe this is the tiny path by which water is coming, and water would be coming in this way. But the moment it crosses this opening, it just diverges. Now you can see it is diverging, right? So here what we are seeing is positive divergence. So if I consider my water to be vector function, so I am using the initial letter W to represent it. So for this particular case, I am going to write that this is del dot W greater than 0, because water is just spreading out. It is covering maximum space when it passes through that tiny opening, which is our surface. Then you can see this particular case also, the second pic. Here, forget about the curls and rotation of water, because that we would discuss in curl. Here you see huge amount of water is coming, but then it's just converging. See, it's converging. This whole quantity, this whole amount of water was coming, and then it converges to a very narrow opening. So now when water passes through this narrow opening, which are these tiny holes, it would converge. Greater amount of water is coming, but after passing through this tiny opening, it would simply converge. It would follow a narrow path. So what is happening here? Basically, this is the example of negative divergence. Okay, negative divergence. So this means that either the fluid is constantly flowing towards the point and its density is increasing. See, in this particular case of positive divergence, density is decreasing because the amount of, you can say, the water molecules, now they have more space. Density is what? Mass per unit volume is density. So same amount of water is here, but now they have more space. So if volume is more, if denominator is more, then density would be less. Inverse relation between density and volume. So now same amount of water molecules, they have more space to go. They are capturing more volume. So their density is less. What is happening here? Here same amount of water molecules, now they have very small volume to go through. Now they are, after passing through the hole, they are capturing very small volume. So smaller the volume, higher the density. So usually whenever we find sinks, we would observe negative divergence. We also call them negative source. Okay. Here I can mention this del dot W is less than 0. This is the example of negative divergence. So whenever you find sinks, that means you are going to experience negative divergence, because sink is, what does it do? Actually, whatever amount, huge amount is coming, but then it simply just drains out through that opening. And then let's have a look at this third example. You can see here the shape of the pipe and then the shape of the water that is coming out. Here you can see that whatever amount, whatever volume of water was coming before passing through this opening, same amount, you are not seeing any divergence, there is no divergence, there is no convergence, same flow. So water would be flowing like this and now it is flowing like this. So it has not changed its flow at all. That means there is no divergence. So this is the case of zero divergence. So I will write here that this del dot W is 0. So that means the divergence of this vector is 0. The flux entering any volume is exactly the same as that leaving that particular volume. So in case of fluid, zero divergence means that as much liquid leaves the volume as it enters it. Whatever is the volume of liquid entering, same is the amount or volume of the liquid leaving. So neither there are sources nor there are sinks in the field. So in case of positive divergence, we often say that there are sources present. There is some source. Whenever there is source, so what does the source do? Source provides you something and sink takes from you. Okay? In normal sense, source always provides you something and sink takes something from you. So in case of positive divergence, we say that sources are present. What they are doing? They are just diverging the amount of water or fluid flowing. When in case of negative divergence, sink are present. So what they do? They simply converge the volume of fluid flowing. And in case of zero divergence, there are no sources nor no sinks. So they would not provide anything extra. They would not take anything extra from you. So the whatever is the amount of incoming, same is the amount of outgoing. This is the case of zero divergence. And we also say that a vector function whose divergence is zero, that is called solenoidal vector. So in this particular case, this W is solenoidal. Only here, right? And now this, coming back to this picture, glory hole, what do you think? Which of the types of the divergence does this picture show? Now, huge amount of water is there, and then whole of the water, they are just passing through some narrow opening, and then they would continue flowing through that narrow opening. This is the example of negative divergence. You can see the sink. So whenever you see something like sink, which is just sucking the fluid out, then that would be the example of negative divergence. So this is the case. So this glory hole is basically giving us the example of negative divergence. Here also you can see another example. Someone has just tried, I just got this picture from Google and it is also explaining it really nicely, that you can see this portion here. You are not seeing any source, no sink, because water is just flowing normally. So if you consider a particular portion, whatever amount of water is passing or entering in this portion, same amount is going out. So this is the case of zero divergence. Here, where the water is actually falling down from the tap, this particular region, right, the circle in red, this portion. Now from the tap, the water is flowing here. So you are seeing, you know that there is some source. That source is tap. Now what is happening? The water is following this narrow track, and then just after flowing this, it is spreading. Can you see this? It is spreading in all directions. So if something is spreading out, it is diverging. So that means this is example of positive divergence. And we have a source as well. And then you see the sink here. Now what is happening? This huge amount of water that was present, when it passes through this portion, it converges. So basically here, all the fluid flowing, this vector function is converging to the point. They were having some wider space available. So they were flowing through this whole portion. But now once they move through this opening, they would follow a very tiny track, a narrow track. So this is example of negative divergence, and we have a sink there. This is the meaning of sink. And they have used the actual sinks that we have in kitchen to understand the concept. This is how we understand divergence. Okay, and I think by understanding it with the help of water flowing is the best way to understand, because that actually gives us the best idea. This was all about divergence, its physical significance, And now in the next video, we'll again use our mathematical approach to understand divergence in terms of Cartesian coordinates. Since we have to discuss a really important theorem, which is Gauss divergence theorem. So that includes the word divergence. So that means it makes use of this concept of divergence of vector function. So for that, we have to understand divergence in terms of Cartesian coordinates, which we will do in the next video. Thank you for joining me today.